death packet for chi-squared regression, and we're going to be working problems 1 through 10. So in a random sample of 25 high school students, each was interviewed as to GPA and weekly hours worked at part-time jobs. What is the critical t-value in calculating a 90% confidence interval estimate for the slope of the resulting least squares regression line? So essentially what they're asking for, since they're talking about a confidence interval, they're actually asking you to calculate t-star. Now, one thing to keep in mind when we're working with regression, degrees of freedom are n-2. So our degrees of freedom in this case are going to be 25 minus 2, which equals 23. So we're going to need to go to calculator here, or you can go to a table, but second vars, inverse t, parenthesis, 1 minus 0.90, close parenthesis, divided by 2, and their degrees of freedom are the 23, or n-2, and we end up getting a value of 1.714. And so E is our best choice for that. So the question came up, how did I know to do n-2? Well, I knew that I was working with regression because they're talking about slope. So that meant that I was working with a regression line, and they also indicated it here, but either slope or regression, when we're working with those, the formula for degrees of freedom is n-2. It's just something you're going to have to memorize. That's one thing for all the tests, you're going to need to know how to calculate the degrees of freedom, and regression is n-2. All right, this is number 2. Suppose that scatter plot of log x and log y shows a strong positive correlation close to 1. Which of the following is true? First off, when we're working with logs, a log graph has a curve to it. So if the log of x and log of y show a strong positive linear correlation, it means that we're working with a nonlinear relationship to begin with. So consequently, the variables x and y are going to be non-linear, all right? So in this case, a scatter plot of the variables x and y will show a strong non-linear pattern because they're going to show more of a log pattern, all right? And I'm gonna pause this. All right, number 3, we have 3 scatter plots, and it says which of the following gives the proper ordering. And we basically have the correlation coefficients, and they go, well, which one gives the proper ordering? So let's talk about this real quickly. First off, this one has a very strong, this is going to have a high R, but it's a negative. So this is going to be pretty close to -1. This has a positive, but it's not going to be as strong or as close to 1 as this one. And this one is a very loose pattern, so it's going to have an R equal to about 0. So first off, this is going to have the smallest. So R2 is going to have to be the smallest. So we need to be looking at the ones that start with R2. And then after that, the next smallest R is going to be R1. The next will be R3 because it's positive. And then they say take the absolute, they put R2 in absolute value signs. And the fact that it has the absolute value signs means this is going to be close to if I take the absolute value of this, it's going to be close to a positive 1. It's not a positive 1, but it's getting close. So the absolute value of the -1 turning into a positive, my best answer is going to be C, because R without the absolute values is close to -1. This is close to 0. This is between 0 and 1 somewhere, between 0 and 1. And then, and I guess I should put 0 less than R3 less than 1. And then the absolute value of R2 is going to be pretty close to 1. This is going to be close to 1. And please remember, correlation coefficients range from -1 to 1, with -1 being a perfect line in which all the points lie on the line. That would be r equals -1. And then r equals +1 is an upward slope with all the points lying on the line. And okay, this is number 4 on the death packet. And number 4 says, consider these points. And this one doesn't have the y value, so we only have an x on this one. What should n be? So what should this y value be so that the correlation between x and y is r equals 1? So we want perfect correlation, which means I need to have every single point needs to be on an upward slope and every single one of them needs to lie on 1. So basically, I need to get the regression equation for these points. So I'm going to get the equation y equals a plus bx. And once I have that, I'm going to plug in 10 for x. And I guess I should put a hat on that and calculate what the y value is. So I've already input the data, and I'm going to go stat test, linear regression t-test. My x list is L1, my y list is L2, choose my not equal. I'm going to store my regression equation in y1, and I'm going to go alpha, trace, enter. Okay, so at this point, I have my A, I have my BX, and I'm just going to scroll down, and I notice something. I notice my correlation coefficient is R equals 0.999. That's not R equals 1. So in fact, when I go to graph it, and I'll do this right now, second stat plot, and I have X list, Y list, and I'll go zoom 9. That line is close to those points, but the line doesn't lie on those points. If you remember in geometry, 3 points define a line. Well, guess what? These 3 points are not, they're not on a line. And if they're not on a line, you can't fix it. So consequently, because the initial 4 points are not on a line, you cannot add an additional point and make it 1. It'll never, ever be 1. And it might get closer and closer to 1, but it will never, ever become 1 because not all those these four original points aren't all on the same line. Had these 4 been on the same line, I would just plug in 10 for X and solve for Y hat, and that would be fine. But in this particular case, they're not all 4 on the line, so we can't fix it. And there's nothing we can do about that one. All right, 4 pairs of data are used in determining a regression line, Y hat equals -2 plus 6X. If the 4 values of the independent variables are 37, 52, 18, and 23, what is the mean of the 4 values of the dependent variable? In other words, let's plug in our x's into this equation. Let's plug in 37 and calculate y 52, calculate y 18, calculate 23, and calculate, and we're going to take the average. So I'm going to kind of cheat and do that fairly quickly. I've plugged in 37, 52, 18, and 23 into the calculator. I'm going to go up to the top of L2. This is cheating. You don't have to do it this way because you can actually plug them in individually and solve it. But I'm going to go -2 plus 6 times L1 because that's where my x's are. And it calculated my y's for me. Then I'm going to go stat calc, one variable statistics. My x list, the list I'm interested in, my y's are in L2. And I ended up getting an average of 193. But basically all you need to do is plug in 37 here and you should get 220. Plug in 52 for X and you should get 310, 18 and get 106, and then 23 and get 136, and then take the average of those 4 numbers. And so that way number 5 would be B. So the question came up, what did I plug into the top of my calculator in order to populate my y's? So here's what I did. Basically, our y hat equals -2 plus 6x. Well, L1 has my X values. So I could rewrite this equation and go Y hat equals -2 plus 6 times L1, because that's where my X's are in L1. So I'm going to go up to the top and I'm going to plug this part in. So -2 plus 6 times, and then L1 is in second one. And I'll press enter, and then it populated and gave me all my Y's. So these are all my Y values. Once I have my Y values, I'm going to go stat calc, one variable statistics. My list of Y values is an L2, so second two. And that's my average. Now it says X bar, but this in this case is going to be my Y bar. This will be my average of 193. Number 6, data on the number of cancer deaths among Americans in thousands of years since 2001 result in a regression line. And by the way, you can actually do this where you put your Y variable here and put a hat on it. So my predicted deaths equals 550 minus 6.05 times the number of years, because this is my Y variable and this is my X variable, with an R of equal to 0.863. What is the correct interpretation of the slope? So this is what I'm interested in. Well, please remember, slope is the change in Y over the change in X. All right, change in Y over the change in X. Well, that's not, I can't admit them right now. All right, change in Y over the change of X. Well, my Y variable is, my X variable is years, my Y variable is deaths. So I'm really having negative 6.05 years over, I'm sorry, I wrote that wrong. This is deaths over 1 year, right? So negative 6.05 deaths over 1 year. And these are in thousands. So I can multiply this number by 1,000 and I'm going to have negative 6,050. So for every 1 year increase, the number of deaths is dropping by 6,005. Now notice they included the word average, because remember, this is a predicted amount. Some years are going to be more, some years are going to be less. So on average, it's dropping by that amount. That's not necessarily what it's going to drop in any 1 year. It could go up in 1 year. It can go down at more than that in 1 year. But on average, we have a change or decrease in the number of deaths of 6,050 for each 1 year. All right, number 7, one of my least favorite questions, to be truthful with you. To the right is a scatter plot with one point labeled X. Suppose you find the least squares regression line, which of the following is a true statement. And they want to know, so the first question is, X has the largest residual. Well, remember, the residual is a plot of the data that's going to be centered at 0. All right? And some data is going to be above the line, some are going to be above the line, and some are going to be below the line. And truth of the matter is, I don't know what the linear equation is going to be for this, but chances are it's going to be a horizontal line. And this point will have, this point here, this point here, and this point here will all have greater residuals than X. That X might be on the residual line. So that's not going to be the case. X is an influential point. We like to keep that definition of influential points to linear equations. And in this case, so it is not an influential point. There will be no pattern to the residual plot. No, we definitely don't have a linear graph. And because we don't have a linear graph, there will be a pattern to the residual plot. X is an outlier. Again, we like to, in our case, we are using this, an outlier tends to be an X value that's too small or too large. Well, it's right in the middle. So this is not an outlier because it's in the middle. So in this case, as much as we hate that answer, none of the above are true statements. All right, so the question came up with, how did I know to draw a horizontal line? And the fact of the matter is, maybe I didn't. So consider this. Consider you take this set of points to a bunch of elementary students and you give them a ruler and say, I want you to draw a line to as close to as many points as possible. All right, I want you, well, you're probably going to get a line that looks like this. And you may get a line that looks like this. Or you may get a line that looks like this. And you may get a line that looks like this. So basically, you end up with a bunch of lines with a bunch of different slopes and with all different directions. And so at which point you're telling me beta 1, the slope, is 0 because we don't know the direction to draw the line. And which is what equation has this? Well, y equals 0, which is the horizontal line. So that is why I drew a horizontal line, because we really have no idea which direction is the best way to go with that. Or another way of saying, for this one, the correlation or the linear correlation would be approximately 0 because it's not a linear graph. Okay, so number 8, suppose the correlation between two variables is 0.85. If each of the variables is multiplied by -1, which of the following is true about the new scatter plot? So what's going to happen? Well, all we're doing is multiplying the y values by -1. So consequently, the direction of the slope is going to change. Now, if we multiply them both by -1, there is no change. But multiplying by one side by change, we're going to change our slope, and we're no longer going to have a positive slope. We will have a negative slope, and consequently, we will have a correlation of -0.85. The correlation level is not going to change because because they all shifted together. So all we did is we're going to be just as close as we were to the regression line, but our direction of our line will change because we only changed one of the variables. Consider this. Once again, our equation for slope is change in y over change in x. Well, if every single data point were on the line and all I did, so if every single data point was on the line, we'd say we have an r equal to 1. Well, if I multiply this by -1, I now have an r equal to -1. So the same, this is analogous to that. But instead of having an r equal to 1, we have an r equal to 0.85. So all we did was say, hey, -1 times this, and we just switched the direction of our correlation from positive to negative. I'm sorry, I forgot to say that it slopes down and the correlation is -0.85, so that's B. Number 9, this is I would star this. This has some very useful information in it. So which of the following statements about correlation coefficient of R is incorrect? It is not affected by the measurement units of the variables, and that's true. It is not affected, all right? And so if I multiply all the y's by 3, there's no effect. If I multiply all the x's by 3, there's no effect. If it is not affected by which variables called x and y, that is true because the relationship is the same. Now the equation is swapped, but the relationship is the same. So that's also a true statement. It is absolutely impacted by extreme values, all right? It absolutely is impacted by extreme values. So that's a false statement. So this is gonna be my answer. It absolutely gives information about a linear relationship, but not causation. Just because we have a correlation does not mean it's causative, because we don't know if an experiment was run. Now, if an experiment was run, it can show causation, but generally speaking, for a linear, when we're working with these, we're working with surveys and samples, and we haven't done an experiment with, so consequently, it's difficult to show causation. R, remember, tells you how close the data is to the predicted line. So when I'm close to the line like that, we're going to be close to 1. and this obviously is a positive. On the other hand, if I'm all over the place and not anywhere close, I might get closer and closer to zero. So it just tells you the strength of the linear relationship and how predictive it is. So this was also a true statement. And it always gives value between -1 and 1, even if the association is nonlinear. That is true. It'll always be between -1 and 1. Obviously, if we end up with a parabola, we're probably going to be really close to 0. That would be the correlation in that case, because the relationship was nonlinear. All right, so number 10, a linear regression analysis performed on the data from 2 scatter plots A and B, resulting in identical least squares regression lines with positive slopes. Which of the following statements is true? All right, so we have 2 identical equations. Well, I can have 2 identical equations, and one can have a graph. That's not going to show up. Unfortunately, I don't have the appropriate graph color, the appropriate sticky notes paper today. But I could have this one. And you can see the data points are pretty close. I could end up with exactly the same graph, and my data points be all over the place and not very close. But I would still have the same y-intercept and slope, even though the data points aren't very close to the line. Now this one right here is going to have a correlation that's closer to 0. This is going to be closer to 0. R will be closer to 0. And this is going to be close to 1. This isn't really going to be close to 0, but closer to 0 than that one is. The correlations do not have to be equal. Obviously, we just said that. If the sum of the squares of the residuals in A is greater than the sum of the squares of the residuals in B, then the correlation in A will be greater than the correlation in B. Generally speaking, we want to minimize that. However, this is a ratio. It's how close it is relative to the distance traveled. So consider this. I have a prediction line that looks like this. And it happens to be, I don't know, arm spread versus height. So if I want to predict height versus arm spread, I end up getting a pretty nice graph that looks like that. Now let's just say this was measured in inches. And I decided, you know what, I'm going to change it. I'm going to measure it instead of inches, I'm going to measure it in centimeters. Well, guess what? To measure in centimeters, I'm going to have to multiply every data point by 2.54. So it's going to move farther away from the line. But the correlation would be exactly the same because it's actually the same data. So in this case, C and D are not accurate. E is my best choice. All right. I hope that helped. So the question, the comment was made, hey, I thought the sum of the squares of the residuals equals 0. And that's close. The sum of the residuals equals 0. And remember, the residuals are above and below the line, so we sum the residuals, they equal 0. So we square them so that they don't equal 0, because we're going to have positive and negatives when we sum residuals. With the squares, you're going to have some below the line, some above the line, and so we're squaring them so that they won't sum to 0. So they kind of give a measure of variance.